conference in Barcelona, NIPS. So I urge you to look up Google deep learning if you're not familiar with it, and look at the amazing work that people have done with computer vision. But I'm really happy to introduce Sasha Rush from Harvard. He's done amazing work with deep learning and NLP, applied to all kinds of wonderful, mostly text data, but also images as well. So,
Hi everyone, my name is Sasha Rush. It's great to be here in New York. I have two artists as parents, and they were bummed when I told them as a kid that I was going to be a scientist. But I think kind of their dream occupation for me on a Friday night is to be in the village talking to you guys. So this is like the closest I'm going to get to Berlin. So it's kind of fun to be here. I'm going to talk to you about work that my group's been doing for the last year. I've been a faculty at Harvard for about a year, and when you start, I think as faculty, it's important to have a little bit of a teen rebellion moment. And my teen rebellion was to get obsessed with this model known as seek to seek. It also happens to be the model that pretty much everyone's been obsessed with for the last year, which has been really fun. And what I'm going to do today is I'm going to give a research talk, but I'm going to play a lot of covers. And a lot of the covers are going to be kind of from a lot of really great people who have done a ton of great work, including Professor Cho here at NYU. But I think it'll be kind of good to talk more about the high-level stuff and give you a sense of what's exciting about this area. And then I'll dive in the second half of the talk to some of the more technical aspects. So we'll start pretty high level, and then we'll get to some technical detail. I would be amiss if I didn't talk about my students. Yoon Kim and Sam Weissman are my graduate students. Hendrik Strobel is a postdoc who I work with quite closely. Yoon Kim Dang is a guy who just sits on my lab. He showed up one day and we didn't kick him out. Alan Schmaltz is also at Harvard. And all these talk slides, including many variations of this talk, are on GitHub. So let's start with this sentence. The room was not very light. A small oblong reading lamp on the desk shed glow on polished blank. So pretend that you're not here on Friday night. Let's say you're at like Upright Citizens Brigade, and I ask you to just yell out, what comes next? What's here? What's the next word in this sentence?
Wood.
Wood? What was it?
Floors.
Floors.
Bagel.
Bagel. Was it chip? Shoe.
Glass.
Glass. Stone. Yeah. So kind of roughly all concrete nouns, things that like are either reflective or not reflective. Any other guesses?
People.
People.
Water.
Okay, so let's do what I do whenever I have a problem. Let's ask the internet. So this is from the Google Ngram viewer. And this is the phrase unpolished blank over the last 200 years. And they keep roughly what you guys gave. So unpolished surfaces, unpolished wood, unpolished and, I guess that's a not noun. Unpolished rice, that's a little weird. Glass, stone, stones. So roughly it was relatively good. We were able to kind of just guess from our guesses what people were doing, kind of the Family Feud version of the problem. So this sentence is a pretty famous sentence. It's from this paper from 1948 by Claude Shannon. And I'm going to talk to you a lot today about neural networks. And neural networks are a pretty old idea, but actually Shannon's predates that. So this is predates a lot of things, predates some of the work on, say, the Turing test and a bunch of other aspects. But this paper is the central paper to a lot of fields. I think it's actually pretty important in the social sciences. I don't know too much about it, but I know that people in the social sciences use the word noisy channel, and we use that word too. And this is the kind of stuff Shannon was defining. And particularly, he uses this sentence as an example of a game where people would try to guess the next word or the next letter. And what he's really interested in is how many guesses are needed to predict that word. And kind of conversely, you can think about that as how you would estimate the probability distribution of the next word conditioned on the previous word. So WT conditioned on W1 through WT minus 1. Okay? Kind of a silly problem. And Shannon goes into it in some details. He builds a kind of model based on counts. He babbles some nonsense sentences. You can go read the paper. It's really fun. It really holds up very well. So yesterday I was reading the New York Times, and I came across this article. And I know the New York Times is kind of a, I don't always trust it, but they were talking about AI. And they had this headline, and it's called The Great AI Awakening. And if you read the subhead, it says, how Google used artificial intelligence to transform Google Translate, one of its more popular services, and how machine learning is poised to reinvent computation itself. So I've been working in natural language processing for a decade now. And let me tell you, it's not every day that the front page of New York Times Magazine talks about my little sub-niche area of the world. And so this was really cool to see. What I'm going to talk to you today is pretty much how the thing that's transforming AI and the world and computing and all these kind of big buzzwords of deep learning comes down to this problem that Shannon talked about over 70 years ago. So let's start by kind of getting concrete. I'm going to talk to you about deep learning. Deep learning is a rebranding of neural networks. Neural networks are a pretty old idea, not as old as Shannon, but certainly something people were talking about in the 60s. I'm going to talk about these three things, and these are going to be the three types of neural network tools I'm going to talk about for the whole time. So first I'm going to talk about embeddings. Embeddings are maps from sparse features to dense features. So we go from, say, an indicator vector in a very high dimensional space to one in a much lower dimensional space, say 100 to 1,000 dimensions. That's dense. Then I'm going to talk about RNNs, or recurrent neural networks. And these go from sequences of dense features to a representation of that sequence. And finally, I'm going to talk about softmax. And softmax just maps from some dense features to a discrete prediction. So that's how we're going to get a probability out of these models. So we're going to do language modeling. So we're going to, given a sequence of words, WT minus 3, WT minus 2, WT minus 1, we're first going to map them to what are known as embeddings. You can think of embeddings as something like this, and let's see if this works. So for every word in English, we're going to map it to a vector. I'm then going to project those, say, 100-dimensional vectors down to a 2-dimensional space and show you what they look like. So here we have every word in English, and the distance between these vectors is roughly going to correspond to how similar the neural network thinks those words are. So here we have things like construction and capital, employees and operations, funds and company. We can zoom around this space and see how it maps these words down to these representations. So person, people, film, story, etc. Now, these representations were one of the first ways that we in NLP started using these methods from neural networks. But I think the methods we're going to talk about in the talk move way beyond kind of just using these word representations to being able to use representations of multi-word sequences. To do that, we're going to use a recurrent neural network. So here we first map each one of the words to a vector, and then we apply the following transformation. At every time step, we combine our last hidden state, ht minus 3, with a new word, say xt minus 2, to create a new hidden representation, ht minus 2. And to do that, people use relatively complicated functions. But for the sake of this talk, just think about this as a single neural network layer. That is, we apply an affine transformation, so a linear applied to our word representation, a linear applied to our hidden representation, and a bias. And we apply a nonlinearity, such as a sigmoid. And that produces our new representation of what we've seen so far. Now, the final stage is to make a prediction. And the prediction we're going to make is what the next word is. So that is, we're going to take our hidden representation, ht minus 1. We're going to apply another linear, and then we're going to apply a softmax. And that is going to give us the probability of the next word, or our estimate of the probability of the next word, given all the previous words we've seen so far. Furthermore, we're going to say the probability of our sequence is just the product of each of those predictions along the way. Okay. So we get back to Shannon's formulation here. Instead of simply just counting up the words we see, we're going to learn a neural network to predict the distribution over the next words in order to do language modeling. Now, at this point you might be saying, okay, fine, we can predict the next word. That in and of itself is not that useful. But it turns out that slight variations of this model are incredibly useful. And within the last 2 years, we've seen variants of language modeling dominate many different natural language tasks and provide almost a unified form for solving many different problems. So this work first started in machine translation. And this is work that was first at NIPS 2014 and IClear 2015. This Sutskever paper and work by Cho here at NYU. Very similar ideas then rapidly spread to many other problems in natural language processing. So things like question answering, things like parsing, things like very basic conversational agents, all started being developed using very similar methods. And that's part of what I'm going to talk about today. Now, all of these sequence-to-sequence models are variants on exactly the language model that I previously showed you. And the variants look like this. So instead of modeling the probability of just the next word, we're also going to condition on some arbitrary other piece of data. We're going to call that data X. So we're going to model the probability of a sequence of words conditioned on an arbitrary input data. And then we're going to just try to use that probability distribution. Now, in translation, it looks like this. So here we have a picture where we're mapping from a Turkish sentence to an English sentence. We're going to simply run a recurrent neural network over the Turkish sentence. We're going to call that X. And then we're going to condition the probability of the next English word on the previous English words we translated, and also that Turkish sentence. So we're doing exactly the prediction problem that I talked about earlier. We're trying to get a distribution over what we think the next word is. But instead of just using the last couple words, we're also going to take into account the fact that we know what the original Turkish sentence is. That's going to help us narrow in on that guess. And I want to really emphasize, though, that when you do translation, you often think about it as just thinking of a map between an input sentence and an output sentence. But really, a huge part of translation is producing a coherent, fluent sentence in the target language. So being able to do the original language modeling problem well is crucial to doing the translation problem well. Now, I would be remiss again if I didn't talk about all the details that matter here that aren't really going to be important for the talk, but I want to point out. This only works if you make these models really big. So these little, like, I'm showing you like boxes of 3 vectors. In practice, they're much larger. They're like 1,000 dimensions, and you have kind of 1,000 by 1,000 matrices doing these transformations. You also have to stack a bunch of them on top of each other. So I'm showing you 1 layer, but in practice, people use 4 layers. On top of that, you have to use variants of the recurrent neural networks I've shown. In particular, a variant known as an LSTM is crucially important to getting a lot of this stuff to work. And finally, there's a bunch of details that kind of are represented by these little glyphs in these slides. The way you do the conditioning of the source sentence matters. You often want to kind of have a distribution over which word you think is going to matter for the next translation. And you have to incorporate that in to do really good high accuracy translation. And there's a bunch of other details. But again, if you're interested, I can point you to references. They're not necessary to the talk. Yeah?
Can you just expand on the last point you just mentioned? You have distribution.
Yeah, yes. And actually, I'll show you some pictures of this later. When you're doing translation, in a very simple word, let's pretend every Turkish word has 1 English word. You have to deal with the fact that you have this, you have all these Turkish words that affect your translation. So what people often put in here is what's called attention, which is a layer that gives you an expectation of all the vectors of your source, given a distribution of which word you think is going to matter next. So you have, basically, you can think of it as like a map that tries to point you to the part of the sentence you think is going to matter for translating the next word. Okay. Actually, this is a good place to stop. Are there any questions about the basics of this model? Because I'm going to spend the rest of the talk going into detail. Yeah?
Well, it's a very simple question, but when you train this model,
Yep.
do you need multiple translations, or does it actually just use like the Turkish base and the separate Turkish and English corpus?
Yeah, that's a great question. Sorry, I often talk to NLP audiences, so I didn't go into too much detail there. The other crucial aspect to these models is they need a tremendous amount of data. So for translation, we often use 2 million up to 10 million pairs of translated sentences. So we're going to be learning all the parameters. That goes all the way down to where we put the vectors in that space from data. Yeah?
Where do you get that data?
So for translation, there's a long history of collecting data. The original translation data came from this data set called the Hansard's corpus, which consisted of the Canadian Parliament, which by definition has to be in English and French. Later, they founded the EU just for the sake of collecting more data. And in the EU, I think it has to be in 16 different languages. Since that point, the US government got interested in this. This company down the street called Google got interested, and a lot of data came out. Yeah. Cool. Any other questions about the model? Yeah?
You mentioned the sigmoid
Yeah.
sort of distributional assumption, I'm guessing. Lynn and Ted Marcus from the recent paper that is quite critical of like log normal and sigmoid sorts of distributions in the case of criticality. You know, that NLPs frequently don't fit the tails of the extremes of these languages well.
Yep.
So I don't know if you have.
I have literally no response to this. This is entirely an empirical decision, and there is no theory involved in this aspect.
But with the sigmoid curve, there is an assumption of the distribution, the shape of the distribution.
So I want to make two assumptions. So one, I'm actually not using a sigmoid as the output. So I'm not doing like logistic regression here. I'm using sigmoid inside of multiple nonlinear transformations of a neural network. So once you do that, literally all the theory goes out the window. We're not even trying to fit a linear model here.
But the criticality is extremely dominant.
Yeah. I think your question is probably relevant. It's not going to be covered in this talk, and I don't have a good response. Yeah.
I noticed you use a four-layer LSTM.
Yep.
So typically, how do you choose the four? Is it just an empirical process? Do you try 3, 4, 5, 6, and just?
So normally what we do is we wait for Baidu to write a paper, or Google, and they just literally do this just incredible great search on these models to figure out. Oh, sorry, it was a joke. No. there's not a great way of figuring out architectural hyperparameters for these models. People have proceeded in this realm to get 1 or 2% gains just by trying lots of things. I joked about Baidu because they tend to do this pretty intensely. Yeah.
Each industry has its own vernacular. So,
Sure.
for example, in the finance industry, if I tell Google buy 5 GD35
Yeah.
calls,
Yeah.
it translates that into Hebrew. Intellectually, it thinks that calls are conversations as opposed to call options.
Yeah.
But a finance person would never say call options.
Yeah.
So how do you deal with that kind of idiomatic problem?
This is actually a really great question. I'm not going to cover it too much here. In practice, people have begun to train these models with the following idea. Let's say you knew your data was broken into you had some training data that was finance, some that was sports, and some that was from blogs. You could literally just prepend to the source side a token that tells you what domain you're in. And then at the test time, you knew that this was going to be finance. You could literally just pretend that and translate it in a finance vernacular. So it's almost like you'd be treating finance like a sub-language in the language you're using. This is very recent stuff, though, and it seems to be quite interesting.
Is that better than having multiple
It turns out it's better than having multiple models because you get more data because you can train one model on all of this data. And so if you have just a little bit of finance data and a lot of regular data, train them together. Okay, one last question and then I'm going to move on. Okay, I'm going to move on. Great. Let's see. Okay. So I mentioned that over the last year, my group has become really interested in these models and the fact that they perform translation so well. In the process of getting fascinated by this, we built a system. The system is called OpenNMT, and it's a fully open source implementation of this idea. And here we go. Okay. So you can go and play with these models in real life. So here is our implementation of this idea. You can kind of use it for various different products or different research aspects. One thing that's really neat, though, is that people have been doing machine translation for a very long time. Over the last 10 years, a form of machine translation developed called statistical machine translation. It was actually simpler than what came before, but still very complicated. So there are open source implementations of it, but they're almost 50 to 100,000 lines of code. And they're just kind of messes of different Perl processing scripts and language-specific ideas. This version of machine translation was written by my graduate student in about a couple months, and then taken by a company that does translation, known as Systron, and cleaned up. It's about 2,000 lines of code. But what's remarkable is that it performs at par with all these systems, and actually at par with what Google Translate has been doing. So the stuff that we're talking about, transforming computing and AI, is just downloadable. It's just 1,000 lines of code. You can read it. It takes a while to train, but it's roughly what I just showed you. So the mathematics behind these things are not that complicated. It's democratizing in a way that anyone can play with these models and do relatively well. So I'll leave a pointer to that. As an example, this company, Systron, actually posted a website online that has this model running for about 32 different language pairs. So it seems to be down now, so you can play with this. And I want to emphasize that not only do these models work pretty well and they're pretty simple, they perform much better than all the previous translation systems before them. So the Google Translate model you can play with now online is significantly more fluent, particularly in very difficult language pairs. So pairs like translating from English to Japanese or English to Hungarian are way better than anything we've had ever for these kind of systems. Now, I mentioned that
what language is it written in?
Ours is written in Lua/Torch. There are others written in Python, but I would caution that while Lua is different than what you might be used to, it's very similar to Python, so you can definitely figure it out if you're interested. Cool. So, okay. Cool. Now, I mentioned that this similar technique works for many other problems in natural language processing. And I'm going to mention some of the ones my group has worked on. So this is stuff that we've done at Harvard. The first is using these models for summarization of text. So this problem we call neural summarization. The idea is to take a long sentence, such as Russian Defense Minister Ivanov called Sunday for the creation of a joint front combating global terrorism, and then translate it into a shorter sentence, like Russia calls for joint front against terrorism. So summarization is a particularly important task in natural language processing. It's used for a lot of applications, such as like multi-document compression or just kind of different generation type tasks. But most of the models people use for this task would just pick or choose words or sentences from the original. When you apply these models, you allow the system to do all these abstracted changes, such as changing Russian Defense Minister Ivanov just to the word Russia, or to do power phrases like changing for combating to the word against. And since we published this paper, it's become a particularly popular task in NLP. A bunch of other people have improved upon our work. And one really cool application is we actually work with the Washington Post to use this method to generate example headlines for their articles. So they build into their CRM a little plugin that would suggest headlines for a given article. Now, that might give you a hint about how we train this model. To train this model, we had to go on a hunt to find a very large amount of data that we could train the model to summarize with. So what we did is we found about 4 million newswire articles. We took the first sentence as the foreign language and the title of the article as the target language. And we trained the model to just learn to translate from English to English on this data. Second application is grammar correction. So here, given a sentence like, there is no doubt tracking systems has brought many benefits in the information age, our aim is to translate it to a correct sentence. Oh, yeah?
Sorry to keep interrupting you, but I have a question about the summarization part. How do you know if the summarizations are actually good?
So how would you know if you were a human, or how would you know automatically?
Automatically in general, because if you run this on a focus, it's an unsupervised process. So in general, it's used for
why do you say it's unsupervised?
well, I mean, it is supervised because of the natural use measure.
Yep.
I guess if you're getting references, you don't have any real labels. These are your approach for.
Oh, yeah. So both for summarization and translation, you use these kind of, you call them like n-gram-based Hamming distance metrics. So you count how many unigrams, bigrams, trigrams, 4grams were the same as your reference data. And then you check the length is roughly similar. That's kind of the standard people use for these tasks. I'll talk about this metric later called BLA. That's the kind of the main one. And there's also one called British. Cool. Yeah.
Again, just sort of maybe humorous comment.
Yeah.
So let's say you take the Washington Post articles and train it on its Washington Post headlines.
Yep.
Let's say you take the New York Daily sort of rag articles, but then you apply each to the other. So you get what the Washington Post article would be for the Daily Post, vice versa.
Yeah.
It might actually be kind of amusing. And then, of course, you can also generalize it like what would the Rebar news site say for the Washington Post article, vice versa.
Yeah.
And you can start another tweet storm
Right.
and become very famous.
Well, we're academics, so our goal is, I hope to get grants and not become famous. But I think what you're saying is somewhat interesting, and there's actually been a whole kind of storm of creative AI type approaches, mostly in image recognition, of people kind of doing silly stuff like this that's
I think it kind of comes off from music, like you want to play
yeah.
the style of Mozart.
Exactly. And there actually are great websites where you can take any painting and map it to the style of a different painter or something like that. And actually, it works quite well. I mean, I wouldn't be fooled that it was Van Gogh, but it's cool looking. Yeah. Okay. Awesome. Okay. So the second application, pretty different, but we're taking a sentence that may have grammatical issues, extra words, agreement issues. And we're running this system to try to produce a corrected version. So this is a grammar correction without any notion of the underlying language. We just got a large corpus, about 400,000 corrections from, I think it's from a press. So it was from a press that worked on this problem, and they corrected things. And by doing this, and we actually added an extension that got to look at the letters of the word to find spelling mistakes as well. But basically, off the shelf, the system took first prize at a grammatical correction competition. So without any kind of knowledge of what a grammatical mistake is, just trying to learn when you want to change something in the system itself. Okay. So the last application I think is probably the coolest, but this is a very different type of application using exactly the same code. So here we were saying, well, this X as input doesn't have to be a text at all. And in fact, a lot of people have been doing really cool work on what's called image caption generation, where you take an image and try to generate a caption for it. But we said, why can we take, say, an image and try to generate markup that would generate that same image? So here we run a neural network over an image itself, and the output of the model is going to be LaTeX. So we scraped about, I think about 200,000 archived papers for formulas. We then got the random image of those formulas and tried to generate the LaTeX that would produce them. And let me see if this demo works. Cool. Okay. So this is the system generating the LaTeX from the image itself. So this is kind of a form of OCR, but it's very different than traditional OCR because, for one, we're never segmenting the image itself or getting training data that maps the letters to the symbols. We're simply just taking the full image, training it to try to generate the LaTeX that it saw in the data. And a bunch of these. Let's see if I have another. So that's roughly